Welcome. In the last class we saw an important aspect or an important concept that we will use repeatedly in classical thermodynamics, that is the concept of state variable values not depending on the path taken between the two states. To understand that a little better, the example that we had considered was taking multiple routes between two destinations 1 and 2 in a mountainous region, and if we are interested in the difference in heights between 1 and 2, let us say, then the height being a state variable which depends only on the state of the system, or the state 1 or the state 2 and not on the path in between them, irrespective of the path that we take, the value of the difference in the state variable or the difference in heights in this case will always be the same. This is a very powerful concept or an idea that we will repeatedly use. This route where the altimeter was available gave us a means of measuring. Similarly, we would have routes in thermodynamics between two states, various paths, and one of those paths would have some easy way of measuring the state variable between the state variable values at these 2 points. This was one important aspect. Then we started looking at equations for a closed system, useful thermodynamic equations for a closed system. Let us start with that again for this particular class. We had just done one last time. For a closed system, we have already seen from the definition of enthalpy H from equation 2.1, enthalpy, it is defined as U plus PV. Therefore, the total differential of enthalpy dH is d of U plus PV, and if we use the rules of differentials, it will be du plus, using chain rule here, it will be first function into derivative of the second function plus the derivative plus the second function into derivative of the first function, that is pdv plus vdp, and we already know du is tds minus pdv, that was our equation 2.5 earlier, and if we substitute this here, we have tds minus pdv plus pdv, so these two will cancel out and we have dH equals tds plus vdp. This is equation 2.6 that we ended up with the last class. There are other useful equations or relationships that we can derive for the other thermodynamic variables, and let us see some of them here. If you recall the definition of the Helmholtz free energy A, we had defined it as U minus Ts. If you want, you can go back and check equation 2.2 in your notes or in the video lectures. A equals U minus Ts. Therefore, the total differential of A, following the same scheme earlier, is nothing but du minus, by chain rule, Tds minus SDT, and we already know that du equals tds minus pdv from equation 2.5, and therefore if you substitute tds minus pdv here, tds minus pdv minus tds minus sdt, tds minus tds will get cancelled out, and therefore we are left with dA equals minus sdt minus pdv, and we will call this equation 2.7. So we have looked at internal energy U, enthalpy H, Helmholtz free energy A, and the only other thermodynamic variable that we have defined so far is the Gibbs free energy G. According to our definition of Gibbs free energy, G equals H minus Ts, enthalpy minus the product of temperature and entropy. Same scheme as earlier, dG equals dH minus tds minus sdt. We know that dH is tds plus vdp, this we have already seen when we derived equation 2.6. Now if we substitute TdS plus VdP for dH. You can see that this TdS and this minus TdS will get cancelled out, and what we are left with is dG equals minus SdT plus VdP. Let us call this equation 2.8. Remember, we have derived these equations for a closed system. It is useful to see all these equations together. So let us see that, and it is nice to have it in one place for reference later. Therefore, let us do that now. So for a single component, single phase closed system, the following equations are valid, which we just derived. Du equals TdS minus PdV, this was our equation 2.5. dH equals TdS plus VdP, equation 2.6. dA equals minus SdT minus PdV, equation 2.7. dG equals minus SdT plus VdP, equation 2.8. Usually these useful relationships become a part of us because of repeated use, but for examination purposes, for your university examination purposes, you might want to remember these equations. You can always derive them quite simply from first principles, as we have shown. So far we had looked at a single component system, 1 mole of that system, and that being a closed system. Now let us slightly complicate the system. Let us increase the number of moles of the pure component. Okay. Earlier it was 1, let it now be more than 1. It is still a closed system, it is still a pure component, and only the number of moles are more than 1. If that is the case, remember we had used U, S, H, A, G for 1 mole of the substance, the thermodynamic quantities for 1 mole of the substance. Now since the number of moles are greater than 1, let us use a slightly different terminology so that there is no confusion later. So the terminology for the thermodynamic variables of a system consisting of, let us say, n moles of a pure component is U total, represented as UT, S total ST, H total HT, A total AT, G total GT, and V total VT. The 4 equations that we derived for a closed system earlier, for 1 mole of a closed system, a closed system consisting of 1 mole of a pure component earlier, are valid even in this case. I am not going to prove that in this particular lecture. If you need proof, you can see one of your reference books, which is by Kenneth Denby. Let me just state the equations here. DUT equals TDST. Remember that T is an intensive variable, its value will not depend on the amount of substance present, so it is going to be T. T DST minus P dVT, P is also an intensive variable. Let us call this equation 2.5a. DHT is TDST plus VT dP, equation 2.6a. You can compare these equations with the equations for 1 mole of a pure substance. DAT equals minus ST dt minus P dVT, equation 2.7a, and DGT equals minus ST dt plus VT dP, which is equation 2.8a. To re-emphasize, these are the equations for a system that consists of n moles of a pure substance and the system is a closed system. Now let us look at a slightly higher level of complication. Let us stick ourselves to one phase, let us say a gas phase or a liquid phase, just one phase there, but now let us increase the number of components from one earlier. If you had only one component, it was a pure substance. Let us increase the number of components from one to many. Now we have a multi component system, but still let us work in single phase. Therefore we are looking at a multi component system, but a homogeneous system. For example, it could be a mixture of gases of different species. It is all going to be in the gas phase, but it is going to consist of many different species. The air is a very good example of a multi component homogeneous gas phase system. Air has predominantly nitrogen, oxygen, but you also have carbon dioxide, you also have water vapor, and so on and so forth. So this is an example of a multi component homogeneous system. Let us look at some of the relationships that will be useful for a multi component single phase system. Before we do that, we need to know some terminology that we will use here. Let N1 be the number of moles of component 1, N2 be the number of moles of component 2, and so on. If you recall our equation 2.5, du equals TdS minus PdV, you can recall that we took the internal energy U as a function of S and V. It will become clearer when I say the next thing, and for saying the next thing, let me extend this to a k component case. This U as a function of S and V that we took to write for equation 2.5 was limited for a single component system or a pure substance. Now we are extending this to a k component case. Since it has k components, it has to be indicated by the total internal energy, and let us say that this is a function of entropy, total volume, and since it is a multi component system, it will definitely depend on the number of moles of each component present, and we are taking k components to be present. So N1 number of moles of the first component, N2 number of moles of the second component, and so on till Nk number of moles of the kth component. We will call this equation 2.9. Therefore the total differential of ut, if you recall the way the total differentials are written, is the partial differential of ut with respect to St at constant other variables, or at the conditions where the other variables are held constant, which is Vt, N1, N2, N3 are all held constant, which is indicated by Ni being constant. So dou ut by dou St times dSt plus dou ut by dou Vt, the second variable, at constant St and all Ni times dVt plus dou ut by dou N1 dN1 plus dou ut by dou N2 dN2, and so on and so forth, and which can be indicated in short form as sum of I equals 1 to I equals k, because there are k components, dou ut by dou Ni at constant Vt, St and Nj dNi. Note that the subscripts I and the subscripts j do not correspond to the same species. We are taking the partial differential with respect to one of the species when all the other species are held constant. This is a notation to indicate that, and this will be consistent. This will help us in developing a consistent notation for representing this kind of a situation throughout the course. So summation of I equals 1 to k dou ut by dou ni Vt at constant Vt St and Nj times dni. This is the total differential. This comes from the theorem in mathematics where you can represent the total differential by this particular thing if it is an exact differential. We will call this equation 210. If we compare the first two terms of equation 210 that we just wrote down with equation 2.5a, I am going to give you both these equations now. This is 210 that we derived just now and this is 2.5a. Here going by the same scheme, dut is dou ut by dou st at constant v dst minus dou ut by dou Vt at constant St dVt. Okay. It is quite easy to see the correspondence between the two, and therefore it is quite straightforward to write dou ut by dou St at constant Vt Ni equals the temperature, and dou ut by dou Vt at constant St and all other components, the number of components being held constant, as minus P. Note that this is for a multi-component system and we have compared it with a single component system and we are drawing useful relationships. See you in the next class.